My name's Gay Stewart, and we're here to talk about how some of the things we say to make things sound easier actually make things much harder for our students to learn. A little introduction. I first created this talk because this is a personal set of pet peeves of mine that Karen Jo can tell you I've been whining about for years, and that we actually tried to fix with the AP Physics redesign. We all know how well that went. But Tiffany actually took my workshop last summer and revised it and gave it at the AAPT meeting because I just had twin grandbabies. And she's chair of the AP Physics 1 committee, and she was my student, my advisee all the way through. So nice family photos there. So some of the words in here are, Tiffany said, I wish you'd say it this way. Just a little bit before, because some of you know me and have known me for a long time, and some of you are like, who is the crazy fuzzy-headed lady at the front of the room? So I just want to give you a little introduction. I'm going to flash some slides that have lots of words on them that I'm not going to talk about a lot, but just the number of words are going to impress you with all the things we did. And basically the idea is I love physics. My high school physics teacher just turned me on to it, and then I went off and I was doing weird things in college, and I found my way back to physics. Went to grad school thinking I wanted to be an awesome physics teacher who also did some research, found out that's not what the average university physics professor thinks of themselves as. So did some resets, and ended up getting to live my dream, getting a job at a university where my primary job was to figure out how kids learn physics and help them do it better, and also teach some physics. First thing I had to do, though, when you get to higher ed is I had to write a proposal to get the National Science Foundation to give me money, because that's the only way you get to keep your job. And my first program officer was someone named Ruth Howes. She's going to come back. So the good things we did at Arkansas, we really reformed our introductory physics courses, giving the students an opportunity to interact with their peers, all the things we know are good. Right? If you were in the plenary this morning, kids remembered 10% of what they read and 70% of what they say. So having the kids talk physics to each other, argue, and figure it out was very important. And we also saw this eventually serving as an excellent ultra-early field experience. We were producing more high school physics teachers from just our campus than most states, which was very fun. And they were really good teachers. One of them was Tiffany. And the thing we figured out is if you teach your own classes at a university the way you think teachers should teach, the kids learn more and you end up with way more physics majors. So when we'd gotten to Arkansas, they were graduating between 0 and 2 physics majors a year. We started trying to improve the preparation of physics teachers, and we ended up graduating 30 majors a year, which may not sound like a lot, but for a physics department, that's actually fairly huge. And it continued after the funding for the program ended. So that caught some attention. And then, so that first grant where we reformed the physics class, Ruth House was my program officer, and a year later I get a phone call from her saying, how would you feel to get your hands on a national college curriculum? And I'm like, colleges are full of crap. There's no national college curriculum out there. We just don't play well together. And she goes, there is one. And she told me all about AP, which my high school had not had. And my kids were not quite to the age yet where I knew what that was. And I was like, well, that sounds fantastic, but there's no way in the world those people would ever come ask me to do anything. The next day, I got a phone call saying, Gay, we've been told about you. Would you be on this committee? And I knew I'd been set up because I just told her that I would, of course, do it if anybody ever asked me. So 96 was the phone call. 97 to 2003, I was on the committee. I chaired it. I ended up the chair of the College Board Science Academic Advisory Committee, which led to the redesign of the sciences. And then a whole bunch of things happened with that, up through me being the chair of the Physics 2 committee. and I still wish I'd chosen to be chair of the Physics 1 committee. We started these redesigns with a lot of research behind us and recommendations from the research that if you're going to teach a science class, you should actually teach it based on what we know about how kids learn science, that should be at the forefront. And this study came out and everybody looked at it as condemning AP Physics and the IB a little bit. But if you read the words, what they said basically was they were the best things out there, and their problem was that they were too much like the average college course, which is of course what they were shooting for in order to get placement for their students. And so taking this report to the president of College Board, we said, why can't we just be the best college course instead of the average? So that redesign was informed not just by that national study, but we looked at college curriculum because we do still have to get the kids college credit, national and state standards, and the other thing was this idea of learning by design, right? Kind of backwards design to make sure that we were getting at the learning outcomes we wanted. There was a whole bunch of steps in there, and yeah, I was like on all but one step of it. So, and it was, this was important. We were funded by the National Science Foundation, and the program officer would come to our meetings. I was co-chair of the redesign, and I would tease her, and I would also give her homework. We made her fully part of the redesign process. But she said NSF was paying for an AP redesign out of the Division of Undergraduate Education because they were hoping we would shame colleges and universities into doing a better job. Okay? Certainly my own children were told, get every AP class you can, because I know that high school teacher, I know how they're going to feel about you. And if you got to take classes at college, talk to me first before you pick a. For some reason, they both skipped my class, but they both took their dad's class. So, but they got AP credit for mine. They said it wasn't because I was a bad teacher. It was just because they had a good AP Physics teacher in school. But the idea was not for us to lay out a test or a curriculum necessarily, but to what should it look like that kids can learn, and to make sure we knew what those resources would be needed, so that whatever school a kid was in, there was a pathway to them learning the skills we laid out. We didn't want to lay out something that you could only do at a school that had that $10,000 a student he was talking about. How many people choked when he said the average expenditure on a student was $10,000 a year? I was like, I can tell you it is in my state. It's not that. There's one school. So we're looking for increased depth of understanding of essential concepts, wanted to make sure they could develop the capacity to use critical skills, make sure we were using the current research on learning, instruction, and assessment, establish coherence within and across the disciplines. As we've redesigned the redesign, that part's kind of faded out a little bit because it's hard to get the committees to talk to each other as much as we could when we had NSF money, so we could pull everybody together and say, chemistry, that's not the way physics talks about energy. Well, you guys talk for a while, which is what we were doing during the redesign. Again, creating learning programs accessible no matter what schools the kids were at, and preparing students for success in those subsequent college courses, because again, a lot of kids take AP, the school makes AP available because of that, if you take this, you can get out of this when you go to college. Again, the increased depth of understanding of the essential concepts, of being able to really learn how to reason, that's where you take the skills that, it's not just learning the physics, it's learning how to learn that'll be valuable to you in everything else you do. So that was a major focus. And if you think about it, there's expert level of thinking. There's a real disparity between what teachers know and what students know. And, sometimes those words or concepts, if we leave out a few of the words, the kids don't even see the connections anymore, right? And so instead of this nicely organized graph that an expert has where everything kind of hangs together and there's just a few things that things are stuck off of, with students, you get kind of a patchy set of things that aren't connected, right? And these are the words that I've been saying, but this is the green part Tiffany added to point out that the thing I've been saying for 15 years, Kip said at some point. I don't know. I think I said it first. If we leave out some of the words to make a concept sound easier, we end up leaving out those connections that a student needs to fit the pieces together. And when I was an undergrad, my advisor's wife was doing a study on how people learn and why a lot of really smart people drop out of science in college. And this idea that, you know, the average person thinks physics is a million little pieces you have to memorize independently, instead of sort of these big ideas where things hang together. And I spent a lot of time focusing on how to unpack this in energy and systems, because it turns out they're just so cross-cutting across all the standards. And there's some nice research out there to build on them. And if you look, there's it's a cross-cutting concept in the next generation science standards. I know Texas has its own, just like West Virginia does, but it's really at its guts. There's, you know, some similarity. Lots of connections with AP. And you know, both emphasize that the system definition and how we think about the energy interactions and measurements depend on that system definition, right? So if we never start out with, okay, this is our system, then everything after that becomes harder to see how things compare. And just, you know, saying the same thing in other people's words a couple times, right? If we simplify things, we actually increase confusion. So I'm going to skip to some examples. And again, email me. I'll send you all this if you want all those references and all the pretty slides, so you can argue with people about why you need to put a few more words in your homework assignments, which I had. As I was getting on the plane on the way here, a friend of mine who's an AP physics teacher texted me and said, I teach with this other teacher, and he doesn't want to put the extra words in. So we have this problem. Let me show you this problem. I was like, well, yeah, you didn't define your system, and you asked for the potential energy of the elevator. What are you thinking? And he goes, well, my best student walked up and said, am I supposed to do the work by gravity, since I'm just talking about the elevator, or do I do potential energy? And I said, that's the whole point. And you guys are going to get beat to death with that in the next few minutes, so I'll skip it there. But it was exciting that the last thing before they closed the doors on the plane was me going, yes, read chapter so-and-so. Okay. So there's some common wording. We're going to go through some examples of that generate incorrect models. And I'm going to show you some problems where those incorrect models have surfaced, and that's some of the examples I put out of some of the AP problems, but you see the pictures, you're going to know what we're talking about. And we're going to talk about how some small changes in wording, if we're consistent and use those 4 or 5 extra words every time, can really help students create a more coherent understanding, so they learn one big thing. And here's some cases where, okay, in this case, this part's 0, and in this case, this part's 0. And they understand why, instead of memorizing all these different things, which is what they do now. And I tell the kids, my memory is terrible, so I can't memorize a bunch of stuff. I got to know how it all fits together. That's why, I can't do chemistry. You know, because we really want the kids to see how they hang together so they can develop that robust problem-solving approach that's going to work every time. And I'm going to throw in a couple of models that are really important, particularly because maybe not everybody in the room is an AP teacher. In AP, we use object very particularly. We use it the way some people use point particle or point mass. There's a bunch of different ways. But it turned out that if you read through the average college textbook, when they used the word object, about 80% of the time they meant it the way we meant it, but they never defined it that way. So we just thought, we're just going to define it and make people talk about their models. And we'll see why that's important in a second. So here are some of the simplified statements and the misunderstandings they lead to. Potential energy of the ball. My teacher always used to say that. My textbook said that when I started out in school. But it leaves students to believe that that object by itself can have potential energy. And then they have no idea when to talk about gravitational potential energy and when to talk about the work done by gravity. And in fact, the thing that led me into this, I'd only been teaching for a couple of years, and somebody who'd had my class had gone and talked to somebody, and I get asked to do the professional development for a 6th grade science class that's going to have to teach physics, and they're all terrified. But they had their favorite demo that they did. It was a roller coaster. And they had work done by gravity, or the Earth, and gravitational potential energy, both in their equation. They'd never noticed it was wrong because they weren't doing it mathematically. They were doing it qualitatively. And so, of course, both of those things were affecting it correctly. But if they'd ever done the math, they'd have realized they had way too much energy going in, or twice as much energy going into the system. And so when I explained it, they said, well, how do you know? Which one are you supposed to use? How do you know? And oh, well, if you start with defining your system, right, you can only have potential energy if you've got something you can change its shape. Work equals force times distance. How many of us have ever said this? Okay. It's confusing for students because they don't actually know what that distance is, and they don't necessarily know that you mean it's an external force, right? So just putting in those extra words can help them understand when they get to use the equation. This one was complete shock to me, but somebody from another organization came up that had done a huge study. We use the word act. That leads students to believe that forces are independent things. So they're their own thing out there. It's like this category of actual thing, not describing an interaction. It's out there. It's coming to get you, man. And that goes into the whole them believing there's still a force on something after you let it go. The force of the hand keeps with it because they think forces are their own thing. So trying to very carefully always use a force is exerted by this thing on this thing really helps the kids get away from that. I throw it up in the air and the force of the hand has to stay upward on it until it gets to the top, right? Which is what most of your students will tell you. The other thing is writing down work equals minus the change in potential energy. I mean, those two things are equal, but at different times and in different descriptions of the system, right? So if the force is external, I talk about the work. If I put whatever's causing the force inside the system, the same interaction, I would have a negative change in potential energy, and those two things are equal. But if you just write that equation down, the kids say, oh, I can do both at the same time. Oh, but it's zero, so nothing happens. Yeah. So I've already kind of hit on this. But the thing that really gets me about this is if you talk about the potential energy of the ball, we're all going to get the question right because we know what it means. But either you know what it means or you don't. And so the kids that haven't figured out our magic decoder ring are just left out. It was really funny. I have a friend who teaches at Harvard, and he went around to his fellow faculty members and he asked them a question. And a not insignificant number of PhD physicists at Harvard got it wrong for like a half a second. And then they immediately do the conversion in their head and give you the right answer. But that's because they have a lot more familiarity with it. Our students can't make that switch. So, I try to tell kids if you develop the concept of potential energy, and the next generation science standards, we tried to do it thinking about magnets and stuff, but the committee that was actually working, there was, a chemist who was driving the bus, so some of it got a little weird. But I didn't say that out loud. Okay. But, if you give kids two magnets and have them try to push them together, they can believe there's something going on there. And you tell them, well, that's sort of like, if you turn them so they're pulling each other, that's sort of like you and the earth, right? The potential energy can be an attraction or repulsion, but you're changing, in order to get them to push harder, you push them closer together, right? Squeezing a ball, right? If I squeeze the ball jumps when I let it go. Stretching a spring or a rubber band, right? So all these things involve changing the shape of something, right? But our definition of object was something we could not change the shape of, right? Our definition of object is a point in space, so it's all moving exactly the same way and there's no relative motion between any of its bits. So then an object can't have potential energy, right? So if I want to talk about a ball having potential energy, I'm not talking about gravitational potential energy. I'm talking about squeezing it, right? A spring potential energy stored in the ball. And let's see, right? So I just said that. If you can't change its shape, it can't have potential energy. And so, of course, AAAS said, well, we've given a test problem where we asked about the potential energy of a hiker going up a mountain, and you know, the scores on this look exactly fine. The kids who are high performing on the test get it right. The kids who are low performing get it wrong. There's no weirdness. So you know, it doesn't really matter if we just ask for the potential energy of the hiker. Although if you think about it, a question like this, you would expect more than half of the kids to get it right, probably. If, you know, this is a pretty basic concept. So I said, well, have you ever given a problem where the system does matter? And so they had given this problem where they said, okay, gravitational potential energy of a system of two objects. And, you know, it's that if you pull them further apart, you increase their potential energy, right? But if you look at the answers, almost nobody gets it right until you get to the kids who are doing really, really well on the test. You've got to be scoring at the above average on the test to start getting this right. Actually, the answer that wins, it can be increased by bringing them closer together. It doesn't matter about the shape. I mean, the kids are really lost on this one. So you're like, okay, on that last question, the good kids have just figured out when you ask them for potential energy, here's what you mean. And there wasn't an answer, none of the above on the test, so they give you the answer they know you want, right? But we can't tell the difference between the kids who actually know that it depends on the system or the kids who just know that the higher up you go, the bigger you want to say gravitational potential energy is. So that question was somewhat flawed, and I think they've gotten rid of it. So again, from the very beginning in my class, I will beat into kids, potential energy is a property of a system, right? Not an object. If I want to talk about squeezing the ball, then I'm treating that ball as a system because it's something that can change shape. And, you know, for instance, I'll give a problem on a test where I say, okay, you know, the monkey throws the bananas off the cliff. How's the potential energy of the bananas change? And, you know, if the system is this, if the system is that. And so they have to actually, you know, and is their work done, et cetera. And if you harp at them enough, eventually they figure it out. And then the teacher who teaches the junior level class tells me, oh, the kids are so much better prepared when I get them. And but like the argument I've had with people, you throw a ball at a wall, right? The wall doesn't do any work on the ball. The wall's just there. But the ball compresses when it hits the wall, so it changes shape. So the ball itself is storing energy when it hits the wall. And if that comes back, it was an elastic collision. If it doesn't come back, it was inelastic, right? Throw a ball, throw a lump of clay, see what happens, right? What's different is how much of the energy that's stored in the system that hits the wall that you get back. But people love to tell me the wall did work on things. I was like, hon, I can lean against that wall all day long, and it is never going to throw me forward, right? And you can see where kids get confused about what work is when we do things like that. So again, the big harping point for the last 20 minutes. Yeah. When we talk about potential energy of an object, we're simply not giving the kids the support they need to be able to really understand when to use work, or potential energy. Okay. I've beaten it to death. I've beaten it to death some more. But if you always start by defining the system, which one you're going to use is clear, is the point I want to make. And there was an example, and this was a free response question on the 2017 exam. If you didn't get one of the handouts, and you're sitting near somebody that's got it, but basically, you've got a ball rolling on a table or a block sliding without friction. And then there's another example, and they're very careful to show the starting and ending heights of the block. And the whole problem was worth 7 points. The first part of the problem, which is just assessing this diagram, right, where block 1 falls a different distance than block 2 between the 2 points. That was 3 points of the problem. The average on the problem was 2.1 points. Right? So the most basic thing that we thought was the giveaway points at the beginning of the problem, the kids had a lot of trouble with. And okay, so I've already talked object. One more reason to harp on object, you draw a free body diagram, right? And you tell the kids force is mass times acceleration, and from that you can derive that the force times how far it goes is equal to change in kinetic energy. Beautiful. Then next week you tell them work is the change in the total energy. And they go, huh? But it was the change in kinetic energy last week. What's the difference? Right? But when you draw the free body diagram, a single free body diagram, you're making the assumption of that point, the center of mass of that thing. You're treating it like an object. You're calculating the acceleration of a single point. Right? So you might draw cute little things on your free body diagram. I always tell the kids just draw a little square. Think of me. Draw a little square and put the forces on it. And then I have to write, so I'm a little square. And then maybe somebody laughs. You know. The year I dressed up as a witch at Halloween and the kids asked me, why did I pick that one day not to dress up? We got a few more laughs. But some other important models that we don't always explicitly point out to kids, and we use them all the time. You see the word frictionless, or even worse, massless, right? And frictionless, there are very few things in the universe that are truly anything like frictionless. There's a lot of places where we can neglect the friction, right? But if we talk about frictionless stuff all the time and the kids don't realize we're using a model, then next Tuesday, when all of a sudden friction becomes part of they don't see how to put it together. So if we just let them know, we're going to use a model, we're going to simplify it, let's unpack it just a little bit, then they're in way better shape. And yes, it makes it a little scarier the first day, but I saw the example where somebody was interviewing a student, and you know, it was again a throwing problem, or else it was a walking problem. And the kid said, do you want the real answer or do you want the physicist answer? He'd learned how to answer the question the way we wanted it, but he didn't believe it because he lives in a world full of friction and nobody had told him how that affected those equations we just hand them, right? So actually letting the kids in and to see how their own knowledge, their body memory works in physics, that it's not that they're crazy and physics is something different, is helpful. But massless is the one that drives me crazy, because frictionless is just something where there's not just a little bit of friction, right? But massless, you know, does that mean it's just got a little bit of mass? No. It means that it doesn't have much mass compared to other things. The force of gravity on it isn't a big thing. So in the right situation, I can say that something really huge and heavy, I can approximate it as massless, right? So that one's one to be very careful with. And again, the work equals the force times distance. And, you know, by the time, there was one email argument that went on for 8 pages when I printed it out, by the time I actually convinced my colleague that, no, when you throw the ball at the wall does not do work on the ball. Because students are really confused by what that distance is. The statement doesn't say the force has to be external, And, you know, most of us sitting in this room, we look at a problem and we know exactly which force and what distance to use because we know what's going on, but our students don't. You know, and really what we'd like is for students to understand that fundamental definition of work, that it's how much energy gets transferred into or out of a system by an external something through a mechanical process. Because if they understood that, then when they get to thermo, they would understand what heating is, right? Because that's just transferring energy in through a thermodynamic process. But if kids, you know, and God help us, we use the same word for the process and the amount of energy transferred when we're talking about work. So if we're not really careful, we can have kids come out of here having no idea. And if you ever go into a mechanical or chemical engineering junior level class and ask them any kind of a first law question and see what they write down, you know, it's not pretty because they don't actually understand those transfer ideas. And so, again, for me, I always make sure that kids understand that when I use the word force, I am talking about an interaction between two things, right? And if that interaction is with something outside the system, then it's an external force and it can change the energy of the system. And the distance is how far the point on the system on which the force is exerted moves in the direction of the force, right? Because if it's a system, it can squeeze. If I push on a pillow, how far it moves when I push on it is different than if I push on a block, right? Because a block, is like an object, the whole thing moves. Pillow, no. So the kinds of energy, if I push on a block a certain distance and I push on a pillow a certain distance, I'm going to end up, I've put just as much energy into it, but the forms that energy takes within that system are different, right? How far the center of mass of the system moves in the direction of the force, that's that first thing we teach kids about how do we get from pushing on something to changing its energy. Right? Most of us do it, right? F equals ma, and you do the, you know, substitute in the thing for A in terms of X, and we end up with changing kinetic energy. But that only works if the whole thing moves that same distance. And so if it's an object, yes, that works. So separating, okay, first we're going to talk about how we change the energy of an object. Oh, it can only have kinetic energy. What's different if we push on a system that can change its shape? And then we can bring in all those other kinds of energy and talk about the full work. I've already harped on this. But the big thing is if a force is an independent actor, it's really hard to explain where the energy comes from. And again, a force is an interaction, is a way to transfer energy into a system, right? And here was, even when it's just a simple kinematics problem, right? Launching a ball off the edge of a table, it turned out there was nowhere in this problem that you had to do conservation of energy. But the kids who had used conservation of energy somewhere to check their answer or describe what they were doing and like defined a system, nailed the problem. Other kids had trouble even just doing the kinematics. So 2.76 points out of 7. And this was on the 2015 exam. This one keeps coming back in various forms. I think they just had one that looked very much like this. Launch a block, it slides along for a while on a low friction surface, and then it hits a friction, and you know, how far does it go before it stops? And even the kids who used the right equations had trouble using words, right? Because we want kids to be able to talk physics, because we know that 70% of the kids that can talk, you know, you remember things, right? And the thing is, so you might say, well, but you know, they knew it because they could write down the equations, but most of the kids that wrote down the right equations actually plugged in the wrong variables, right? They didn't know which distance was which. So you start wondering, even did that right equation mean they really understood something? So the 2.67 out of 12 might be kind of a high exaggeration, because if they wrote out the right equations, they got some credit, but then they substituted the wrong things in. Okay, so if something does work on a system, it must provide energy to the system. That's what the definition of work is. And you think about it. So the energy when we bounce the rubber ball off the wall, right, that comes from that elastic potential energy in the ball. Here's my favorite. When you run, right, the ground exerts a force on you, right, but where does the energy come from? Right? It's you, right? You're pushing down on the ground pushes back on you, and you go forward. We'll have kids calculating the work done by friction on somebody as they run. It's like, no, that's how much it slows you down. You can stand on the ground all day long and not get launched, right? You have to push. The static friction pushes back on you. It's not, but the thing that's doing work, here there's not work. You're converting your internal energy into kinetic energy. The work is actually friction. It's decreasing your energy, so you have less energy than you are putting in, right, in your run. So the less your feet slide, the faster you go, right? And the dough hitting the ground, same thing, although it's a great introduction to collisions, right? Because the difference between an inelastic collision and elastic collision, it's exactly the same up to the point where you start looking at how much energy gets restored. So, again, careful language can help kids replace a flawed model. And sometimes they come out of 4th grade where they talked about forces, and oh my God, and nobody can fault the 4th grade teacher who all of a sudden has to teach physics when she hated it in college, if she even got it. But carefully using that language and understanding that you've got to help the kids construct the right foundation in order to learn. If the interaction isn't conservative, then you can discuss the changes in the types of energy, right? And if the interaction isn't conservative and it's inside the system, there's no work. It's just energy's getting dissipated inside the system. Okay, and then the other thing, here's this one is one of my favorites. So a thing rolling down a ramp. This is it's 2016, problem 1. It's in the handout. Can you imagine what kind of free body diagram the kids drew for this? Most of them drew a dot. And they drew the force of gravity and the force of friction on the dot. And so they went on to figure out that the work done on the thing had something to do with the force of friction. But the force of friction is not in a direction to accelerate it down the thing, right? So by not understanding that this isn't just an object, right? And that would have worked fine if there was no friction and it was or negligible friction and it was just sliding down the ramp. But the fact that it's rotating, and that if it was only static friction here, there'd be no energy loss, and all that energy would go into rotational kinetic energy as it rolls down. That was so far out of what most of the kids did that this was a less than 2 points out of 7 question. But this is, I get to my other pet peeve, and then we're going to do a little bit of momentum. But when we just write this down and we don't say anything about it, the kids think that both of these are going on at the same time. And even if you tell them they're not, if you just write this down, how many kids listen to every word you say, right? I know I sure didn't the first time. I only got a B in Physics 1 when I took it as an undergrad. But by the time I got out of Physics 3, I was like, oh, okay. But again, and the work, and there's all kinds of things in there, but just don't do that. Again, the kids just don't know which ones to use. So my own choice is I have little bubbles, right? And I put lots of subscripts on things because I just think it's easier if there's subscripts. And I tell the kids they don't have to write all the subscripts, but think of them as training wheels. And if you put the subscripts on, it's easier to find where you make a mistake. So I have the negative, the change in the internal energy of the system. This is specifically thinking about friction. So the change in internal energy of a system when the frictional interaction is included in the system is equal to the work by the friction force if it is external to the system. You can either do it with the bubbles pointing at it to make sure that they understand these are two very different systems, or you can use columns, but something to make sure that the kids don't think you just mean that minus delta E is equal to W every time, because the kids will believe that if you write it down. Again, if you always start with defining the system, you're always going to know which one to use, right? That's what I tell my kids. I'm sorry, I'm giving you the same spiel I give them. The important thing that we often do not just rub our students' faces in until they know it in their souls, right? Work is the mechanical transfer of energy to an object or a system by another object or system that is external to it. We can describe that interaction as a force. And potential energy is when we have a force, an interaction that's inside the system that is conservative. Depends only on the configuration. That turns out to be the definition of a conservative force. And, okay, we've just beat this one to death, but again, that problem 17.4, the kids who started out defining their system and then designed their experiment did great. The kids who didn't, not so much. And when you're looking at a physics 1 test, even one particular variation, you're looking at maybe 30, 40,000 kids at least. And the tests aren't that dissimilar. Okay, last really harpy point, and then we'll have some time for questions. Energy is conserved in an elastic collision. My teachers told me that for years. And I was like, but wait a minute, energy is always conserved? So what's going on? I mean, foundation, right? Energy is conserved. Well, energy is constant in closed, isolated systems. And, oh, Lord, so you might say closed, you might want to say isolated. If you dig into what kids will read in different textbooks, in chemistry, in physics, and even within physics, if you're in mechanics or thermodynamics or quantum mechanics, where all of a sudden you have to include information as one of the things that can't transfer over the boundary, okay? It's just, so using those two words together, the reason we recommended doing that, it's a little bit redundant, but it covers all the definitions. If it's closed and isolated, I don't care if you're a chemist or a physicist or a quantum information specialist, you will define that the same way. So I tend to use the two words together. And if it looks like you lost some energy, there had to be a transfer. Go look for it, right? Energy is conserved. If it decreases, if your coil does something weird, you know there's something sneaking out of the system. The other thing is kinetic energy is not conserved or even constant in an elastic collision, right? Mechanical energy is conserved. Mechanical energy is constant, but the kinetic energy is restored. Because at the heart of an elastic collision, they're not acting like objects anymore. They come to rest, right, against each other. There's a moment where they're in contact, and then they change direction or whatever is happening based on that collision. How much of that energy gets restored tells you how elastic the collision is. If I get it all back, if all the potential energy stored in that collision comes back, then it's elastic. No, I don't. Oh, good. You guys can't see that. My calendar is popping up reminders. Let me close that. It's confusing me. Okay. No matter what kind of collision I have, the kinetic energy is going to change, right? It'll never become less than I need to conserve momentum, right? The center of mass velocity will stay fast enough to keep momentum conserved, but the total kinetic energy of the system is going to decrease in any collision. And the part up until that point will look the same no matter what kind of collision I have as far as energy. It's after that point when I start getting energy back. And which brings to mind, how many of us actually tell our kids what we mean when we say the word collision? Kind of, sort of, right? Collision is another model where we say that all the other interactions are much smaller than the interaction between the things that I'm studying, right? So when two cars hit each other on the road, they certainly are still feeling the force of gravity. There is friction. You got to measure the stripes on the road. You can see that. But at the instant the collision happens, right, the reason we can call it a collision is the force between the cars, the force the cars are exerting on each other is much bigger than any other force acting on them, right?